So in this video I want to introduce the Hausdorff condition. Okay, so the idea here is we've got, well, let's first consider a metric space. Okay, so there's a metric space X, so this is going to be our metric space. And two distinct points. Maybe here's A and here's B. Okay, and then so I'm going to do. I'm going to put some open balls around these points. Okay, so what we're going to do is we'll put R to be the distance from A to B, and divided by 3, say. Okay, so and notice that this is strictly positive, right? Because one of the axioms for a metric space is you've got two different points, and the distance between them is not equal to 0. It's strictly positive. So we said here these are distinct points. So I've got like so, and then we're going to put U is the open ball around A, radius R, and V is the open ball around B of radius R. So the picture's kind of like this. This was our U and this was our V. Okay, so so U and V, they're both open sets. A is the point of U, B is the point of V, and U intersect V is empty, right? So you should check these things completely from the axioms. I mean, you should, well, I think we wrote down as a lemma that open balls are indeed open sets. Yeah, that's something that you should check. And also that U intersect V is empty. I mean, that also needs a quick check, but that follows easily from the triangle inequality. Okay, so yeah, we've got these two disjoint open sets surrounding A and B, and that's kind of a useful construction that happens a lot in the theory of metric spaces. But now suppose that X was not a metric space, it was an arbitrary topological space, and we had 2 points A and B in it, and we wanted to find open sets around them, U and V, like this. Well, it's not obvious that that's possible, and in fact in a second we'll have some examples where that doesn't happen. So first though, I want to just make a definition to encapsulate the thing we were just talking about. So now let X be a topological space. Okay, so we've got a topological space X with a pair of points A and B which are different. And so we're going to say a Hausdorff separation for the pair AB. Here's a pair of open sets, U comma V. A is in U, B is in V, and U intersect V is empty. And we say X is Hausdorff if every pair of distinct points has a Hausdorff separation. And so, of course, the example, by the construction that we discussed a couple of minutes ago, every metric space is Hausdorff which we prove using U is the open ball around A of radius dAB over 3, and V is the open ball around A of the same radius. Actually, yeah, it's kind of a morally, I should say, dAB over 2 here. It's kind of visually a bit more obvious that it works if we have a dAB over 3, but anyway, either will do. Okay, so anyway, Hausdorff, for metric space, any metric space is Hausdorff. But another kind of sort of very minimal example of a non-Hausdorff space. Okay, so we could have X could just be a set 2 points, A and B. Okay, so we had one of the example on the problem sheet where we discussed topologies on finite sets with only 2 or 3 elements. And one example that we had was just this space here, where we've just got 2 elements A and B, and the open sets. Well, remember, the empty set and the whole space have to be open. Don't actually have to have any other open sets, but we could just we could have a space like this, where set containing A is open, set containing B is not. Okay, this is called the Sierpinski space. Okay, and then there's no Hausdorff separation. For the pair AB, obviously, because if you had a Hausdorff separation, your set capital V, that would have to be an open set containing B. But the only open set containing B is the whole space, and that contains A as well. So your U and your V can't be disjoint. So that's an example of a non-Hausdorff space. Okay, so let's have another example of a space that's not Hausdorff. Okay, so we're going to take this quotient group. Okay, so so like I say, this is the quotient group R mod Q. In other words, that's the quotient set by this equivalence relation, where we declare that X and Y are equivalent if and only if the difference between them lies in the subgroup Q. Okay. So that means we've got a projection map pi from R to X with pi x equals pi y if and only if x minus y is in Q. And it's a surjective quotient map. And we're giving x the quotient topology. So remember how the quotient topology works. That means any subset U of x is open if and only if preimage that's the definition of the quotient topology on a quotient set. You declare that a subset of the quotient set is open if and only if the preimage is open in the original space. Okay. So let's put A as pi of 0, and B is pi of root 2. So root 2 is irrational. So that means that pi A is not equal to pi B, and so these are different. I want to claim there's no Hausdorff separation. Okay, so okay, so suppose we've got two sets, open sets U and V. U surrounds A and V surrounds B. And we want to claim that they don't give a Hausdorff separation. In other words, we want to show that they're not disjoint. So that means that pi inverse u, well, that's open in R, and it must contain, well, 0 lies in u, so pi inverse 0 is contained in pi inverse u. But what's pi inverse 0? I mean, that's just a set of rationals, right? Because pi of x is 0. Pi of x is equal to pi of 0 if and only if x minus 0 is rational. So pi inverse of 0 is the rationals. But pi inverse v and that contains pi inverse b, so it contains root 2. But remember, yeah, so pi inverse v, it's an open set that contains root 2. So that means, because it's open, the whole interval from root 2 minus epsilon to root 2 plus epsilon will be contained in pi inverse v. Yeah, so our pi inverse v, it contains this interval here, but you know it's clear any standard fact about rationals and irrationals, any interval of positive length is going to contain at least one rational number. So we can find it, choose a rational in this little interval between root 2 minus epsilon and root 2 plus epsilon. So that means that q lies in pi inverse v, but that means that pi of q lies in v. Okay, that's just the definition of the pre-image. But q is rational. That implies that pi of q is the same as pi of 0, which is a. So now we're seeing, you know, so pi of q is a, and pi of q lies in v, so a lies in v, and also a lies in u. So we see that so that u intersect v is not empty. So that proves that R mod Q is not Hausdorff. Yeah, so we've had some examples of non-Hausdorff spaces, and you know, from the point of view of geometry and from algebraic topology, they're really quite unpleasant spaces, and we don't want to deal with them. But fortunately, we have shown that all metric spaces are Hausdorff, and that's a good start. But we also had some methods for defining new spaces. We had the subspace topology, the coproduct topology, the product topology, and the quotient topology. And we want so it's good to know that these constructions, or at least the first three of them, they always give us Hausdorff spaces if we start with Hausdorff spaces. So let's prove some things like that. So suppose X is Hausdorff and Y is a subset of X with the subspace topology. So then I want to claim that Y is Hausdorff. So proof, So suppose we've got two disjoint points in Y. Well, as X is Hausdorff, let's call it, we're going to choose two sets U prime V prime that are open in X. With A and U prime, B and V prime, and U intersect U prime empty. U prime intersect V prime empty. So then I put U prime, U is U prime intersect Y, V is V prime intersect Y. So U and V are open in Y, just by the definition of the subspace topology. Then A is in U prime by assumption here, and A is also in Y. That was our original assumption here. So A lies in U prime intersect Y, which is U, and B is in V similarly, and U intersect V. Well, that's just the same thing as U prime intersect V prime intersect Y, which is empty. Okay, so that's that's how it goes, and we can maybe draw a little picture. You're supposed to think if we've got space here. Here's our space X, and then maybe maybe Y is just this part of X, and you've got your points A and B, which are like here and here. And then you start by finding your U prime and V prime, which are kind of like this. And then your U and your V are just the intersections of those with the with Y, which are like this. So that's the proof that the subspace topology is Hausdorff. Okay, so now let's consider the coproduct topology. So let Y and Z be disjoint Hausdorff spaces. And we give the union Y union Z the coproduct topology. And let's recall how that goes. So the open sets are like V union W, where V is open in Y and W is open in Z. Okay. So I want to claim that this is also a Hausdorff space. Okay, so okay, so let's consider two distinct points, A and B, in the union Y union Z. So there's four cases. So case three, case A, 1 is where both of them are in Y. Case 2 is where both of them are in Z. Case 3 is when A is in Y and B is in Z. and case 4 is when A is in Z and B is in Y. Well, let's kind of work backwards. I mean, in case 3, then just the pair YZ is a Hausdorff separation. Okay, because remember, well, I mean, Y we can think of as Y disjoint Y union the empty set, and Z we can think of as empty set union Z. Empty set and the whole space are always open, so yeah, so Y is like Y union empty, so that's of this form here, and so it's open in the union. Z is also empty set union Z, that's of this form, so it's open in Y union Z. So these are both open sets. A is in Y, B is in Z, and of course, as part of our assumption, Y and Z are disjoint. And case 4, of course, works the same way, except just the other way around. So case 1, Y is in that case, Y is Hausdorff. So we can choose a Hausdorff separation in Y. I'm going to call the sets here at capital A and capital B. It'll be more convenient here. So A is in little a is in big A, little b is in big B, and A intersect B is empty. But then remember, A and B, well, they're open in Y, and so A I can think of as A union the empty set, if you like, so that's still going to be open in Y union Z. B is B union the empty set, so it's still there. So these are still open in Y union Z, and give a separation in Y union Z. And then so that was your case 1, and 2 is essentially the same. Okay, so that proves that you've got the union of two disjoint Hausdorff spaces with the coproduct topology. Then the union is also Hausdorff. Okay, so now we've dealt with the subspace topology and the coproduct topology, but let's now consider the product topology. So again, let Y and Z be Hausdorff. Okay, then we want to claim that Y cross Z is also Hausdorff. Here we're using the product topology on Y cross Z as usual. So we have to consider some pair of distinct points, A and B, with A not equal to B. So that means that A we can express as Y comma Z, B is U comma V, say. So here Y and U are in the space Y, and Z and V are in the space capital Z. Okay, so as A is different from B, well, either the sort of Y coordinates must be different, or the Z's coordinates must be different. So in the first case, we can we choose a Hausdorff separation AB for the pair YU in Y. Right? Remember, capital Y was assumed to be a Hausdorff space. Here we're in case 1, so Y and U are distinct points in the space Y here, and so there's a Hausdorff separation. And then we note that A cross Z, B cross Z is a Hausdorff separation. For A comma B in Y cross Z. Let's look at the picture. So you're supposed to think of it, you've kind of got Y along here, Z here, and then this, so your Y cross Z is like this. And then you've got maybe your points, your points A and B. Right, and remember, we're assuming here that Y and U are different. In other words, the Y coordinates of A and B are different. The Z coordinates might or might not be different. But then, yeah, so then we can put, we've got a Hausdorff separation. So we've got our points. So here's our A was in the Y position here. B was in the U position here. Those are different. So we've got a Hausdorff separation, say, consisting of a set capital A here and a set capital B here. And then we fatten them up. This is our point. This is A cross Z. This is B cross Z. And they give us a Hausdorff separation in the product space between A and B. Remembering here that the definition of the product topology, well, the open sets in the product topology can be quite complicated, but the simplest kind of open sets in the product topology are things that are just, open set cross open set. Those are not that's not all the possible open sets, but it's some of them at least. So those were called boxes. Remember, so this A cross Z is a box, and that B cross Z is also a box. Okay, so that's the proof in case 1, and case 2 is essentially the same. Okay, so now we've seen subspaces, coproducts, and products of Hausdorff spaces are all Hausdorff. And we also saw this example of R mod Q. So R, of course, is a metric space. That's a perfectly good Hausdorff space. But R mod Q, we showed, is not Hausdorff. So that's an example to show that quotients of Hausdorff spaces aren't necessarily Hausdorff. So when we deal with quotient spaces, we're going to have to be a little bit more careful to verify the Hausdorff condition in some non-obvious way. That's all we have to say about the Hausdorff condition.